Hello guys, welcome back. My name is Shayog Giri. I am an intern at Intellify, and in this video, let's implement KNN algorithm in Python with Sklearn. As we have seen in the next video, what is KNN, how is KNN used for regression as well as classification, how to make predictions using KNN, and the working rule of KNN as well as the pros and cons of KNN and how KNN fails to give accurate predictions in case of large data sets or large number of input features. KNN is best used, as we have seen, in small when we use small data sets and limited number of input features. As KNN uses distance metrics, it is mandatory for us to scale the features before fitting the model to our data. So let's move on to implement KNN with Sklearn. In this section, we'll see how Python's scikit-learn library can be used to implement the KNN algorithm. Sklearn is just an alias for scikit-learn. Now let's look at the dataset which we will be using. We are going to use the famous iris dataset for our KNN example. The dataset consists of 4 attributes: sepal width, sepal length, petal width, and petal length. These are the attributes of specific types of iris plant. The task is to predict the class to which these plants belong. There are 3 classes in this dataset, that is 3 target variables, as we say: iris setosa, iris versicolor, and iris virginica. So what is the source of the dataset? It's always good to know the source for information. Fisher, RA 1936, the use of multiple measurements in taxonomic problems. The data was collected by Anderson Edgar in 1935. The irises of the Gaspe Peninsula, Bulletin of the American Society, 59-225. So as we have just looked at the description of the dataset, just have a brief look at the snapshot of the dataset. So here is our dataset. These are the 4 input features or the explanatory variables, that is sepal length, sepal width, petal length, petal width. And species represent the class variable or the target variable. Here we have 3. The target variable consists of 3 species: iris setosa, iris versicolor, and iris virginica. So in total, there are 5 columns in the dataset, or 5 variables comprising 4 input features and 1 target variable or the response variable. An ID just represents the column number, the row number, sorry. So let's move on to importing the necessary libraries. Import numpy as np, import matplotlib.pyplot as plt, and import pandas as pd. So what are these numpy, matplotlib, and pandas? NumPy, which stands for Numerical Python, is a library consisting of multi-dimensional array objects and a collection of routines for processing those arrays. Using NumPy, mathematical and logical operations on arrays can be performed. That is, we can perform addition of 2 arrays, subtraction of 2 arrays, transpose of an array using NumPy. Pandas is a high-level data manipulation tool developed by Wes McKinney. It is built on the NumPy package. Its key data structure is called the data frame. Data frames allow us to store and manipulate tabular data in rows of observations and columns of variables. This is the most important use of pandas to import our data set, neither CSV format or Excel format or XLSX format, anything. Importing the data set is the most important application of pandas library. What is matplotlib? Matplotlib is a plotting library for the Python programming language and its numerical mathematics extension NumPy. It is a comprehensive library for creating static, animated, and interactive visualizations in Python. So Matplotlib is a data visualization library. We have other data visualization libraries in Python like SNS or ggplot, as you know. So this NP, PLT, and PD, these are just aliases. NP is an alias for NumPy, PLT is an alias for matplotlib.pyplot, and PD is an alias for pandas. Why do we use .pyplot? If we use .pyplot, then we can use the syntax as in MATLAB. This is just for information. You just remember that while using matplotlib, we have to import matplotlib.pyplot, not only matplotlib. So these are the necessary libraries which we will require. We move on to importing the data set. So here we will use a different method for importing our data set. Instead of downloading the data set into our machine and specifying the path to import the data set, we will just specify the URL of our data set. That is HTTPS, this one within the quotations is the URL of the dataset iris.data. Instead of specifying the URL, you can directly import the dataset using pd.read.csv and giving the path of the dataset in your machine. But here we specify the URL and names. We assign column names to the dataset. That is, these column names we specify as sepal length, sepal width, petal length, petal width, and class, representing the class variable. So we specify the column names to the dataset. So finally, we move on to reading the dataset to pandas data frame. Dataset equal to pd.read.csv URL specifying the URL of the dataset and names specifying the column names. pd.read.csv, as you have noticed, CSV represents the comma separated values, which means that we are importing the iris dataset as a CSV file. So here is PD and alias for pandas. You can see that it is helping us to import this iris dataset into the dataset, which we name as dataset. This is the most important application of pandas data frame or PD. So we import the dataset and store it in a variable named dataset. Now to see what the dataset actually looks like, we execute the following command, dataset.head. So what does dataset.head do, this function? Dataset.head returns the first 5 rows of the dataset. See, first row, second row, third row, fourth row, and fifth row. As we all know, the indexing in Python starts from 0. So here 0 represents the first row, 1 represents the second row, 2 represents the third row, 3 represents the fourth row, and 4 represents the fifth row. So by default, dataset.head shows the first 5 rows of the dataset. We can also specify the number of rows that we want to see by passing a number inside the head function. For example, dataset.head10 will display the first 10 rows of the dataset. Dataset.head15 will display the first 15 rows of the dataset, and so on. You get the idea, right? So we move on to looking at the dimensions of the dataset, that is how many rows are there in the dataset, how many columns. The function dataset.head dataset.shape gives the dimensions of the dataset. It returns a tuple separated by a comma. That is, here in our case, dataset.shape gives 150, 5 a tuple, which means that we have 150 rows and 5 columns in the dataset. As we have seen that the 5 columns here, let's see, 5 columns comprise the 4 input features, that is sepal length, sepal width, petal width, and a class variable. So these are the 5 columns in our dataset. The 5 columns comprise the 4 input features and 1 target or the response variable. Let's do some kind of exploratory data analysis on our dataset before fitting the model. We take a look at the descriptive statistics of the features. Features means these 4 variables. Dataset.describe. We use this function to take a look at the descriptive statistics of the features. So it returns this thing where we get the count, which means the number of rows belonging to each column. So here we see that the counts for all the features are 150. As we have 150 rows in our dataset, we get the means. The mean of sepal length is 5.84. The mean of sepal width is 3.054. Mean of petal length is 3.575, and mean of petal width is 1.19. STD refers to the standard deviation of the dataset, standard deviation of the individual features. Standard deviation of sepal length is 0.828, of sepal width is 0.433, of petal length is 1.76, and petal width is 0.76. Min representing the minimum value of each of the columns. Minimum of sepal length is 4.3, minimum of sepal width is 2, of petal length is 1, and petal width is 0.1. 25% represents the first quartile or Q1. Q1 of sepal length is 5.1, Q1 of sepal width is 2.8, Q1 of petal length is 1.6, and Q1 of petal width is 0.3. 50% represents the median or the second quartile. Median of sepal length is 5.8, median of sepal width is 3.0, median of petal length is 4.35, and median of petal width is 1.30. 75% represents the third quartile or Q3. Q3 of sepal length is 6.4, Q3 of sepal width is 3.3, Q3 of petal length is 5.1, and Q3 of petal width is 1.8. Max represents the maximum value of each column, of each feature column. Max of sepal length is 7.9, max of sepal width is 4.4, max of petal length is 6.9, max of petal width is 2.5. So as we have seen, data.describe gives the descriptive statistics of the dataset. That is, it helps if we are to perform some kind of exploratory data analysis on our data. So now we can see that the values in our dataset are not very well scaled. That is, if we look at the values of the input features, we see that the sepal length has values like 5.1, 4.9. Values of petal width are of the values 0.2, 0.2. So they are not alike. The values are not similar. There is some difference between the values. Petal length has values like 1.4, 1.4, 1.3, and so on. So To do away with this, we will scale the values of the features down before training the algorithm. We use feature scaling. Feature scaling, also known as data normalization, is the method used to standardize the range of features of the data. Since the range of values of data may vary widely, as we have just seen, it becomes a necessary step in data pre-processing while using ML algorithms, especially in algorithms which use distance metrics like the KNN algorithm. Scaling of features is mandated to get proper predictions. So we move on to pre-processing the data. The next step is to split our data set into attributes and labels. Attributes means the input features, that is the sepal length and width and petal length and width, and labels is the class variable, that is the species. To do so, we execute the following command. The X variable contains the first 4 columns of the dataset, that is attributes, and Y contains the labels, as we know. We execute these two commands, X equal to dataset.ilog, and within the argument we push these values, and for Y we do this. So let's understand what ilog does. Ilog selections, it is a position based selection. The first position before the comma represents the row selection, and the second selection after the comma represents the column selection. So let's see what it does. X equal to data.ilog, first selection is all the rows, and column selection is up to the second last column. So we in X, we store all the rows of the data set where the columns are sepal length, sepal width, petal length, and petal width. These minus up to -1 represents up to selection up to petal width. That is selecting the first 4 columns of the data set. Selecting the rows of the first 4 columns of the data set. And in Y, we select all the rows where the column index is 0, 1, 2, 3, 4. That is the class variable. Is it clear? You can refer to this picture for further reference. It will be more clear. Alternatively, we can split the dataset by X equal to dataset.drop class, axis equal to 1, and Y equal to dataset class. This is more convenient as we do not have to deal with the problems arising out of indexing and all. This is more clear to visualize. We drop from the entire dataset, we drop the column whose name is class. Axis equal to 1 means we drop the column class. Axis equal to 0 would have represented the row. So from this entire dataset, we drop this class, and the resulting dataset will be called X. And Y, in Y we store only this column, the class column. So Y equal to dataset class. I think this method is more easy to understand than this one, as we do not have to deal with the problems arising out of indexing. So after splitting our dataset into attributes and labels, we go for the train test splits step. To avoid overfitting, we will divide our dataset into training and test sets, which gives us a better idea as to how our algorithm performed during the testing or the validation phase, as some call it. This way, our algorithm is tested on unseen data as it would be in a production application. So what do we mean by a training and testing set? Training set will be used for training the algorithm, and testing set will be used to calculate the accuracy of our algorithm. This testing set is sometimes also called validation step. That is, we in training set will train the algorithm, and using the trained model and the input features in the testing set, we will calculate the predictions for the testing set, and comparing those predictions with the values of the target variable in the test set, we will evaluate or validate our algorithm. It will be more clear from the subsequent steps. To create training and test splits, we execute the following script. From sklearn.model selection, we import train test split. So what is train test split? It splits arrays or matrices into random test and train subsets. It has many parameters like arrays, test size, train size, random state, shuffle, stratify, and all. But here we will use only one parameter, test size. That is, we execute this line xtrain, xtest, ytrain, ytest equal to, within the train test split function, we pass x, that is the input features, y the target variable, and test size equal to 0.20, which means that 20% of the data will be used in the training phase and 80% of the data will be used for testing phase, training phase. You can play around with this data, like you can use test size equal to 0.3, which will imply that 70% of the data has been used for testing and 30% of the data has been used for validating our model. The above script splits the dataset into 80% trained data and 20% test data. This means that out of total 150 records, the training set will contain 120 records and the test set contains 30 of those records. That is 80% of 150 is 120. So 80% of the data will be used for training and 20%, that is 30, will be used for testing. Sklearn is a free software machine learning library for Python programming language. It features various classification, regression, and clustering algorithms including SVMs, random forests, gradient boosting, k-means, KNN, and dbScan, and is designed to interoperate with the Python numerical and scientific libraries like NumPy or SciPy, which stands for Scientific Python, by the way. This is just for information. Now we move on to scaling the features. As we know, it is a mandatory step when we are using distance metrics for an algorithm. Before making any actual predictions, it is always a good practice to scale the features so that all of them can be uniformly evaluated. Since the range of values of raw data varies widely, in some machine learning algorithms, objective functions will not work properly without normalization. For example, the majority of classifiers calculate the distance between 2 points by the Euclidean distance. If one of the features has a broad range of values, the distance will be governed by this particular feature. Therefore, the range of all features should be normalized so that each feature contributes approximately proportional to the final distance. So, to scale the features, we execute this block of code. From Sklearn.preprocessing, we import the standard scalar module. So what does the standard scalar do? It standardizes features by removing the mean and scaling to unit variance. The standard score of a sample X is calculated as Z equal to X minus U by S, where U is the mean of the training samples and S is the standard deviation of the training samples. Centering and scaling happen independently on each feature by computing the relevant statistics or the samples in the training set. Mean and standard deviation are then stored to be used on later data using transform. This one. Standardization of a data set is a common requirement for many machine learning estimators. They might behave badly if the individual features do not more or less look like standard normally distributed data. That is a Gaussian distribution with mean 0 and variance 1 or standard deviation 1. So we create an object of the standard scalar class and name it scalar. We fit the scalar, we execute scalar.fit extrain. These two lines of code scales the input features in the training set as well as the testing set. We use .fit to scale the features in the input in the training set because we will fit our model in the training set. So after scaling the features, we move on to training and predictions. It is extremely straightforward to train the KNN algorithm and make predictions with it, especially while using sklearn library. We execute this block of code to train our model. From sklearn.neighbors, we import kneighbors classifier, which is a classifier implementing the kneighbors vote. So neighbor-based classification is a type of instance-based learning or non-generalizing learning. It does not attempt to construct a general internal model, but simply stores instances of the training data. Classification is computed from a simple majority vote of the nearest neighbors of each point. A query point is assigned the data class which has the most representatives within the nearest neighbors of the point, which is simply a case of voting. Sklearn implements two different nearest neighbors classifiers. K-neighbors classifier implements learning based on the K-neighbors, nearest neighbors of each query point, where K is an integer value specified by the user. And radius neighbors classifier, which implements learning based on the number of neighbors within a fixed radius R of each training point, where R is a floating point value which is specified by the user. The K-neighbors classification in K-neighbors classifier is the most commonly used technique. The optimal choice of the value K is highly data dependent. That is, it can vary from one data to another. The optimal choice of the value K is highly data dependent. In general, a larger K suppresses the effects of noise but makes the classification boundaries less distinct. So we create an object of the K-neighbors classifier class and name it classifier. We pass the argument n neighbors equal to 5. N neighbors simply represents the value of K in this case, which is an arbitrary value. You can play around with this value of K. Then we fit the model to X-train and Y-train, that is on the training set. So here we use the Minkowski distance. It is by default. The first step is to import the k-neighbors classifier class from the sklearn.neighbors library. In the second line, this class is initialized with one parameter, that is in neighbors. This is basically the value for the k. There is no ideal value for k, and it is selected after testing and evaluation. That is hit and trial method only. However, to start out, 5 seems to be most commonly used value for KNN algorithm. This is just an intuition, nothing else. So after fitting the model, the final step is to make predictions on our data. To do so, we execute this following script. Ypred, that is the predictions, equal to classifier.predict xtest. That is, we use our fitted model, the values of the input features in the testing dataset or the validation dataset to generate our predictions. So the value of Ypred comes out something like this. After making the predictions, we move on to evaluating our algorithm. That is, we have to see how our algorithm performed on this data set. For evaluating an algorithm, confusion matrix, precision recall, and advanced scores are the most used metrics. The confusion matrix and classification report methods of the Sklearn matrix can be used to calculate these methods. Let's take a look at the following script. From sklearn.matrix library, we import the modules classification report, which generates the classification report, and confusion matrix module, which generates the confusion matrix. We print the confusion matrix and the classification report, which means building a test report simply showing the main classification matrix. We pass the values of the y-test and the y-predict. That is, we will evaluate our algorithm by comparing our predicted values and the values of the target variable in the test set. So our confusion matrix comes out something like this, and we get an overall accuracy of 0.97, that is 97%. The results show that our KNN algorithm performed quite well as a classifier in this problem using k equal to 5. 97% accuracy means quite good. Although the algorithm performed quite well with this data set, you should not expect the same results with all applications. As noted earlier, KNN does not always perform as well with high dimensionality or categorical features. That is, if we input the number of input features, our KNN algorithm may not perform so well. A confusion matrix is a summary of prediction results on a classification problem. The number of correct and incorrect predictions are summarized with count values and broken down by each class. This is the key to the confusion matrix. The confusion matrix shows the ways in which your classification model is confused when it makes predictions. It gives us insight not only into the errors being made by a classifier, but more importantly, the types of errors that are being made. So this is simply the definition of confusion matrix. Next, we move on to comparing error rate with the value of k. In the training and prediction section, we said that there is no way to know beforehand which value of k that yields the best results in the first go. We randomly chose 5 as the k value, and it just happened to result in almost 100% accuracy. One way to help us find the best value of k is to plot the graph of k value and the corresponding error rate for the dataset. In this section, we will plot the mean error for the predicted values of test set for all the k values between 1 and 40. So we will choose the value. To do so, let's first calculate the mean of error for all the predicted values where k ranges from 1 to 40. We execute the following script to do so. We define an empty array named error. Then we use a for loop to calculate error for k values between 1 and 40. This code simply does that. In error, we fill this array named error with the values of the mean error. So the mean error array looks something like this. Now we move on to the step to plot the error against the k values. This will give us an intuition on how to choose the value of k. We execute the following script to create the plot. We execute this plot, this graph. These are simply the parameters which you can look up any moment. This is the dimension of the figure. So let's interpret this graph. So from the output we can see that the mean error is 0, that is the mean error are these points. When the values of k values are 2, 4, 6, 8, and when the values of k is between 18 and 33. I would advise you to play around with these values of k to see how it impacts the accuracy of the predictions. It is quite clear that is if we use the values of k from 2, 4, 6, 8 or 18 to 33, we will get a good prediction. That is, the accuracy will be closer to 100%. It might be 100% if we choose a value of say 4 or 6 or 8 or say 19 or 30. You have to play around with this data to see to get the optimal value of k, as it is a hit and trial method. So we implemented the k nearest neighbors algorithm in Python and got to know how to choose the optimum value of k. So conclusion, the k nearest neighbors algorithm does not require any additional training when new data becomes available. Rather, it determines the k closest points according to some distance metric. Samples must reside in memory. Then it looks at the target label for each of the neighbors and places the new found data point into the same category as the majority. Given that KNN computes distance, it's imperative that we scale our data. In addition, since KNN disregards the underlying features, it's our responsibility to filter out any features that are deemed irrelevant. Because if the number of input features is large, KNN does not work well. So finally, we look at where in areas where KNN is used, applications of KNN. The following are some of the areas in which KNN can be applied successfully. Banking system, KNN can be used in banking system to predict whether an individual is fit for loan approval. Does that individual have the characteristics similar to those of the defaulters? We can classify this using KNN. Calculating credit ratings. KNN algorithms can be used to find an individual's credit rating by comparing with the persons having similar traits. Politics with the help of KNN algorithms. We can classify a potential voter into various classes like will vote or will not vote, etc. Other areas in which KNN algorithm can be used are speech recognition, handwritten digit recognition, image recognition, and video recognition. So there are vast applications of KNN as it is a very simple algorithm and very simple to implement. So that's it. That's all for now. I hope you guys enjoyed it. And as I've said, you can play around with the value of K to see how this model works and the algorithm works, how the predictions get improved if we choose a value of K from these values. So you guys try it, and that's it. Thank you.